Okay, so acids. We started to talk about them yesterday, binary and oxy acids. We'll do a whole lot more with those when we get into the chapter on acids. Hopefully we will get to do acid-base titrations. Other reasons we can't just stop everything and do nothing but crystal growth, as much fun as it would be. Names for some common acids are on the bottom of that Ion Bible. I don't expect you to have them memorized, but I expect you to be able to find them and find formulas for them. So if I tell you that you're dealing with sulfuric acid, you can look on there and find that sulfuric acid is H2SO4. What is salt? If I ask anybody on the street, what's salt? What are they going to say? Huh? Thing that you put on your food. And somebody said NaCl, sodium chloride. That's what they're going to say. In fact, what we think of as what we call table salt, common salt, is just one of a class of chemicals. They're ionic compounds where you have a cation and the anion from some kind of acid. So really, they're just an ionic compound formed of a metal and a non-metal ion. In the case of sodium chloride, that sodium cation comes from wherever it comes from. The chloride anion can come from hydrochloric acid. It can come from a lot of places. You can look at carbonic acid, CO3. You can get now sodium carbonate, potassium carbonate. Those are compounds that we work with fairly well. There are some acids that have a little extra, and you get a bicarbonate anion that way. This is not as critical, but we're mentioning it now. We'll do more with salts when we talk more about acids, because they're kind of a natural fit. But it's sort of a what would that be, a preview? A foreshadowing? Okay, we're going to talk about oxidation numbers. When you were a freshman, you probably got a reference sheet that said something like oxidation states. I tend to talk more about charge, things that have actually given up or gained an electron. Oxidation number or oxidation state is a way, oxidation number is a way to talk about, in general, who's sucking up most of the electrons in a compound. It's not an actual formal charge. We're not talking about actual exchange of electrons here. We're talking about uneven sharing. So for a long time, I always said, and these notes reflect my attitude starting out, they're stupid and they're all made up. Who cares? I have increasingly, the more I appreciate some of the subtleties of chemistry, come to appreciate why they're useful. We use them for writing formulas, and you can use them to balance equations. We don't do as much with that because we're mostly dealing with ionic compounds. But they really look at who's gaining electrons, who's giving up electrons, even if it's only a partial, even if it's just uneven sharing. Please don't copy these, unless you feel like you really have to. If you look at the bottom of the new ion reference sheet that I gave you, you will notice an abbreviated version of these 8 rules right there. You get to use that on every test, every quiz, every homework. I think you'd be a moron to try to memorize these 8 rules. Why would you do that? You can look them up. We are externalizing our memory. You realize that, right? And shrinking our brains. I don't need to remember that. I can look it up on Google. Now, the tricky part is, once you use these often enough, you're going to have them memorized anyway because they become part of your working memory, and that's really what we're going for. These are in your book. These are in your notes. These are on your ion reference. Remember that oxidation number refers to how electrons are being shared. If it's a pure element, if it's just an individual atom of anything, they're not being shared. The oxidation number is 0. Pure elements have oxidation numbers of 0. When we look at oxidation number, the more electronegative thing, so the thing that's going to pull electrons towards it, gets the oxidation number it would have as an anion. Okay, so you know what anions most of these things form. If I say bromine, you're going to say -1. If I say Oxygen, you're going to say -2. Sulfur, -2. You know that pretty much off the top of your head, or you're getting better at being off the top of your head. You might have to look it up still. The less electronegative thing gets the charge it would have as a cation. So again, that's pretty simple. It gets tougher when we get into things that aren't as readily known to us, or things that have more than 2 components. So fluorine is great. Fluorine is a hard and fast rule that fluorine is always -1. Every individual atom of fluorine gets assigned an oxidation number of -1. That's easy. Oxygen is generally -2. And that's generally the ion oxygen forms. There are some exceptions. We're not going to talk about them. We're not going to do them. If you go on to do a bachelor's degree in chemistry, you'll deal with those exceptions. You know, they're in a compound with a halogen. If oxygen is bound to fluorine, which I can't even understand how that happens, oxygen ends up with a positive oxidation number. We're never going to do that. We're not doing that. It's weird and it's way above our pay grade. Hydrogen also is sort of variable, but generally hydrogen's 1. It's either +1 or -1. And this is the other big thing that you have to key on. If the compound's neutral, the oxidation numbers have to balance. This is just like balancing charges. Okay? The algebraic sum of all the oxidation numbers has to total 0. If you are looking at a polyatomic ion, the algebraic sum of those oxidation numbers totals the charge. And that's critical. Number 8 is kind of a toss-off. These are really intended to be used with molecular compounds. That's how we will use them. We will not use them with ionic compounds, but the rules can be applied to ionic compounds. And at that point, you're talking about oxidation states. And you can, again, beyond our pay grade, you can get into discussions of formal charge. We're not going to do that. Okay, so I've got UF6, uranium hexafluoride, and I've got H2SO4. So I'm going to start off with the UF6. And when we start doing oxidation numbers, the first thing we do is we go to our rules and we look to see if anything in this compound has a specific rule associated with that element. Is there anything in this compound, and you can look at your little rule sheet, that has a specific rule associated with it? Fluorine. And fluorine's rule is that it always has an oxidation number of -1. Now, there's a really, this is a little bit weird. I've sort of developed this on my own, but I have sort of a standard format for writing these. So, every fluorine has an oxidation number of -1. How many fluorines are there? 6 times 6. That gets us a total negative oxidation state of -6. Write this down. Write this down. There's a method to my madness. Because there are only 2 things here, we know that the total algebraic sum of oxidation numbers for this compound has to be what? 0. So to get a 0, we have to have here +6. Now, how many uraniums are there? Only 1, which means that individual uranium has an oxidation state of +6. Oxidation numbers are typically written not, so note this difference, because it is subtle. This is a charge. This is an oxidation number. Dead center top. Okay? So when we're writing oxidation numbers, I actually do this, down and back up. And it's a good way to structure. It's easy when there are only 2 things. It is harder when there is more than 2 things, when there are more than 2 things. So let's do N2O3. This is what? What would this be called? It's molecular dinitrogen trioxide. Does anything in this compound have a rule specifically attached to it? Oxygen. Oxygen, -2 whenever it's paired with something less electronegative than it. So each oxygen here has an oxidation state of -2. There are 3 of them. And so we get a total negative oxidation state of -6. Algebraic sum has to be 0. So we know this is going to have to be +6. We have 2 nitrogens to distribute that +6 over. So each nitrogen must have an oxidation number of +3. So we have -2 +3 oxidation number. Now those happen to be, well actually nitrogen very often ends up with a -3 charge. So this is not the same as charge. This is just how the electrons are distributed. Notice that the oxidation number of neither of these compounds is 6. We're talking about the oxidation number on each individual item. Let's actually do one more that's just 2 things, and then we'll go on to a trickier one. SiO2, silicon dioxide, I said this is really common in the Earth's crust. This is how you get rocks full of oxygen, but they're not light and fluffy. They hurt when they hit you. Anything in this compound have a rule specifically associated with it? Oxygen. And that rule is -2. We have 2 oxygens, so we have a total oxidation state of -4. We have to balance that with a +4. How many silicones do we have to distribute that over? Just 1. So if we divide by 1, we know that this silicone atom must have an oxidation number of +4. So -2 +4. The numbers that we write up here are not always going to be the same. They're very often going to be very different. If we have different numbers of atoms of different types, they're going to be different. Okay, let's do, so we have 2 tricky cases to do. Let's do a tricky case that only has 2 things first. So we have SO4 2-. What is that? Is that called? That's right, you're looking in the right place. What? No. What's that called? Sulfate ion. This is a sulfate ion. So, does anything in this compound have a rule specifically associated with it? And everybody says together, oxygen! It's like, hey, Norm. Okay, so oxygen -2, we have 4 of them. Therefore, we have a total negative oxidation state of -8. Here's where you have to be careful. The algebraic sum of the oxidation numbers for this compound has to equal what? -2. So blank plus -8 has to equal -2. 6. +6. How many sulfurs do we have? Just that one. So we have +6 -2 for our oxidation numbers. That's one of the tricky bits to remember, is that if it's an ion, it's not going to 0. It's going to equal the negative oxidation number, the oxidation, the charge. Can't get that out. So here we have sulfuric acid, H2SO4, nasty, nasty, nasty stuff. Is there anything in this compound that has a rule specifically associated with it? Oxygen. Now, you have to be careful here. Hydrogen has a rule, but hydrogen's rule is not as hard and fast. So you want to start with oxygen if it's available to you. Okay, so for oxygen, we know that the rule is -2. We have times 4. That gives us a total negative oxidation of -8. Here, we'll do that. Now, do we have a rule associated with sulfur? No. Do we have a rule associated with hydrogen? Yes. What's the rule with hydrogen? Ooh. +1 when it's with something more electronegative, -1 when it's with a metal. Is the SO4 ion a metal? Nope. So that's going to be +1 times 2 plus 2. Now, the algebraic sum here has to zero out. So what are we going to have as our total oxidation on sulfur? +6. We only have one sulfur to divide it by, so sulfur is going to be +6. So if I ask you for the oxidation numbers on each atom in this compound, it's going to be +1, +6, -2. And those don't add up to 0. These numbers are not what you have to get to 0. And that's an important distinction. People make that mistake. These numbers are what you have to get to 0. Okay? This is basically the rationale for me even talking about oxidation numbers much with you. Here's what I want you to realize. Oxidation numbers do have one major use. They have one thing that is used. What I can tell you is I don't know how much it's used. So, we did the prefix system for naming molecular compounds. And you guys are all pretty good at it. It's pretty easy. We like the prefix system. There is another system for naming molecular compounds. The stock system that is used with metals is also used with molecular compounds. It's a newer system. Now, my undergrad chemistry work is 20 years behind me. I'd love to go back and take more, but I don't have the time right now. When I was in school, nobody used stock system for molecular compounds. Every prof I had referred to molecular compounds with prefix system names. I don't know if that has changed. That would be a good question for the chemistry forums, actually. If somebody is unblocked and wants to ask a question. Or I can ask that question. That'll be my question. So I want you to be aware that this exists. When this happens, rather than calling this silicon dioxide, this would be called silicon 4 oxide, because you're looking at the oxidation number on the silicon. Does that make sense? We're not going to use it. I'm not going to test you on it. I want you to be aware that it exists so that if you go on to chemistry in college and they're talking about sulfur 4 oxide versus sulfur 5 oxide, silicon 4 oxide versus silicon dioxide, that you know what's happening. That like somewhere a dim bell goes off in the back of your head and you're like, oh yeah. I don't know how often it's used, but it is out there. We're actually going to stop there for now. I'm going to give you some homework problems that are practice with oxidation numbers. And Monday, there is going to be, before you walk in on Monday, there's going to be about a 10-minute video that I want you to watch. You have a study hall before you come in here. So 5 to 10-minute video on what we're going to talk about on Monday, and I want you to be primed. I will say this, we have lost a lot of time. The crystal thing is cool, but it's kind of become more of a focus than it should. We've got a lot of stuff to cover, and a lot of you are going on to take chemistry in college, and there are things that you have to see before you do that. So we do have to kind of, so it's a little bit of flipped instruction. You're going to have, like I said, a 5 to 10 minute introductory video so you kind of know what's happening, and that will replace the lecture that we would have done walking in on Monday, so then we can just answer questions and do some practice together on Monday. Make sense? Cool.